Good morning, everybody. I'm Matt Gorman. I didn't think I would ever hear somebody excited to talk about data processing. It's definitely a first. So hopefully everybody else is just as excited. So really the intention of this is, like I see it, OSINT's a little bit different. Analysts tend to go get their own collection, bring it back, and then they just go do the analysis. But there's definitely opportunities to scale that. So, taking the Excel spreadsheets on your desktop, I know everybody's got them. I'm guilty too. But putting them in some sort of framework that actually allows you to do much larger scale analysis. So about me, my name's Matt Gorman. I actually started doing analysis in the Army. I was a signals intelligence analyst for 6 years. Got to go to exotic locations, Afghanistan, Iraq, back to Afghanistan. When I was done with that, I just moved into government contracting. So I did that for 13 years, mainly a data analysis focus. Some of it included OSINT, access development, which surprises data analysis as well. So after 13 years, I moved into commercial doing insider threat. And a lot of the analysis is very similar to what I had previously done in government, but you kind of run into this space where there's just all this data, and in commercial, you're kind of doing some of that processing yourself. So it was a little bit different. And now I'm VP of engineering at Pre's a startup. It's using OSINT data to do human risk centric analytics and executive overwatch. So this is the challenge. If you look at the left, this is the intelligence process from Joint Publication 2.0. If you've never read it or gone through it, I definitely recommend it. It's a really good base for intelligence analysis. And kind of what you see is each of the cycles, everything really draws out, here's how this part of the cycle meets the intelligence requirements. But collection and processing and exploitation are actually really slim sections, and they're very important. When I started in data analysis, I started in the analysis and production, and I kind of found I was working my way back into processing and exploitation collection, just because I wanted to better understand, where the data was coming from, making sure that, we were getting the right data. So in these two parts of the cycle, there's definitely challenges, especially with how data has just exploded over, the past 10, 15, 20 years. So you run into these challenges. You hear the 5 V's talked about kind of around if you get into data science circles. So volume, really just the amount of data that's out there. Variety, different formats, different types, different sources. Velocity, it's not only moving fast, it's just being created so fast that it's hard to keep up. Value, does this actually meet some sort of intel requirement for me? Like, is there value in actually going and getting that data? And then veracity, is this legit data? They kind of talked about that in the keynote, like false data, now you're going to have to figure out how to get rid of it. So those are kind of the challenges that we're going to walk through some techniques that, hopefully help you overcome some of those challenges. So we'll start with some of the strategic concepts. So number one, this is another diagram I actually lifted from Joint Publication 2.0. And it really talks about, it's titled The Relationship Between Data, Information, and Intelligence. And really the relationship is just filtering. So if you take that first diagram and overlay it on this one, that's kind of what you end up with is my collection is my filter on my entire operational environment. And then I end up with this bucket of data. Then I have to process and do exploitation on it to turn it into actual information that then I can do analysis and figure out what I care about. And that's analysis and production. So that's kind of where you land on more precision analysis. But one of the things that it doesn't really talk about is there's opportunities to make these other data buckets that you can kind of do some discovery on, be it new apps or whatnot. And those buckets you can actually kind of work together to do, different analysis. It's also helpful for, if you kind of think of those buckets in the context of your intelligence requirements, those are potentially the sources that put you ahead of doing research. But then again, you don't really want to keep tons of it on hand because it represents kind of each step in this process represents more storage, more CPU for processing, which equates to cost, resources, analysts to actually have to go through the data. So ultimately, the goal here is, filter out the stuff you don't need, as far into or as early in the process as humanly possible. Data format consolidation. So on the left, OSINT, this is kind of how I look at OSINT, is you've got all these sources, and then you've got tools that gather data from those sources, and then you have all these formats, but they're all different formats. There's no one federated tool that does, all the collection into a single format. So it kind of gets messy, and you kind of have to come up with ways to beat that. Because really the problem is a lot of those formats end up being very, very big. If you've ever tried to do analysis on terabyte-sized JSON files, it's not a good day. So really the recommendation here is, if you can consolidate that into a single format, it's really helpful. It kind of helps streamline that process. Two other benefits, definitely cost. If you can find something that's compressed, we happen to use a format called Delta, if you're not familiar. It's really just Parquet. It's compressed and has metadata on it. So that huge couple terabyte JSON file gets much, much smaller in storage, saving on costs. The other benefit here is, a lot of the first step struggles in processing data are really, figuring out how do I get this format into my processing. So if you do everything in a single format, it kind of, abstracts that away, makes it easier so you can have analysts come further into the process and do more with that processing, much earlier in the process. Data normalization. This is really about user input. If you ask 4 people on the street or 5 people on the street, in the same location, where are you located, you're probably going to get 5 different answers. Locations are a little bit different because there's this hierarchy as well. So trying to actually locate where somebody or something's at, tends to turn into a challenge. And then you're also working with strings. So the goal of data normalization here is you're trying to get this data into some sort of format where you can actually correlate it across sources. Other examples here, definitely permutations. So if you think about Gmail, it lets you put this period anywhere in a username. So if you're doing analysis on 2 sources, those might not correlate it because one might have a period, one might not have a period. And then also timestamps are another one. If your timestamps aren't really aligned with each other, your timeline analysis is going to be way off. All right, so source and data management. This is really just, doing metrics on your data through the process and then kind of tracking end to end to see what's of value. So in the context of big data, you'll hear people talk about medallion architecture. And really how this is laid out is your first step is what they call bronze, and it's intended to be, completely raw data. So this is where you would actually consolidate your formats. Then your second step is, this is your normalized data. So it fits into your data model. And then your third step is, your analytics. So this actually lines up with the diagram that was, data, information, intelligence. That's kind of the same paradigm here. But when you're doing processing, you tend to lose data between bronze and silver when you normalize it. So effectively doing metrics in that space will kind of tell you, oh, my processing's off. I dropped half my emails. So, back in gold, if somebody's doing analysis on those emails, you've completely lost out. And then just tracking end to end is kind of more return on investment. So if you follow this example, you'll notice that source TGJX never makes it to gold, so it's not even really being used. So if this is your yearly metrics, you've got a source, you've probably put resources on, you're probably doing storage against, it's not even being used, so you can just kind of throw it out. Storage and application, this is really about choosing, what's my final format? Like, where does this need to land to make it consumable to meet those intelligence requirements? Sticking it somewhere where analysts are going to actually use it. Then tools. I'm not going to talk a ton about tools because I think you'll notice there's no OSINT tools on here. That was kind of by design because like the OSINT summits usually that's what they talk about is tools and techniques. But I did include, if you do web crawling, there's some proxy things up there. Scriptproxy is a great framework for kind of scaling those web crawling operations. It'll manage across multiple proxy architectures. Python, I'm a huge fan of Python. I definitely recommend, if you're a junior mid-level analyst, Python is really going to be fire for helping you get through analysis and analytic tasks. Distributed, a lot of things we'll talk about after this will be Apache Spark based. Spark just runs on distributed systems. So it's taking, that single processing code, farming it out. So it lets you do it, on a much broader scale. NiFi, if it's more about data distribution. So if you've got sources kind of spread all over your enterprise, you can use NiFi to aggregate those into one place or one format. And then, data models, kind of already talked about storage. Again, I'll highlight Delta, very good format, easy to use, very flexible. And then we kind of talked about, NoSQL search just a little bit. Really, again, this is like using the tools at your disposal, to do the most with your data. So we'll put some of this together with some examples. So the first concept or example is, how can we take our data that we have and operationalize it, turn it into some sort of enrichment or filter against our other data. The example, kind of the more simple example I think of for this is, when I worked inside our threat, I did a lot of data loss prevention in that mission. And there's like always this desire to understand third-party email domains, which are essentially, this is a domain that a user is using, doesn't really belong to the organization. The user doesn't manage that domain or that infrastructure. So more or less webmail. But finding all the various webmails out there, a bulk of it's the well-knowns, but there's like this trail of kind of unknowns or, kind of more, niche webmails that folks just don't know about. So, looking in the data you have, you can kind of piece through and figure out how do I tell, what's webmail out of the, maybe email logs or whatnot. Or maybe you have some sort of bulk OSINT data that you can sift through to try and figure that out. So you can do that. Another thing you can do is, go look at domain reputations. There's actually some sites out there that they'll have the verbiage that will tell you, hey, this is some sort of webmail domain. So you can definitely take advantage of that. And then you can actually piece those together and you've got this nice data set that you can use to, join to your data to either enrich it or you can anti-join filter stuff out, depending on what the goal is. Proxy spotter, this is actually a man-in-the-middle Python script. So man-in-the-middle is it's a proxy framework that runs on Python. So the goal is I can hook requests or I can hook responses, and then I can do something with them. So really, this was more about web crawling. So I want to be able to take, perhaps new sources or sources I already have, and just throw up a proxy, and then, I can just browse, and it's the same as a web crawl. Doing web crawling, usually think of it in bulk. Like I want to go crawl these 10,000, 100,000 things, but they're more or less the same source. OSINT sometimes tends to be, not necessarily bulk, but it's wide. So if I've got, 50 sources, I want to hit 50 sources, not hit one source in bulk. So something like this, as long as you're kind of set up to do that filtering and pull it in, lets you do that where I can, I don't have to task all these crawlers. I can just go browse and get the same data. It's really good for new web source samples. We'll do a lot of crawling things, but like in order to do that processing code, you first have to go get all the samples. So you can just pull it in, throw it over to, there's techniques. This is actually a GitHub repo, so there's notes on doing some of this. You can actually put it up on cloud storage. If you're using something like Delta, you can then stream it out of Delta to your data processors. So it really expedites the system for getting data from, hey, I crawled this, into the analytic repositories. And then I kind of talked about this a little, it's really good for filling collection gaps. Like I may need this one or two things, but I don't want to go task a crawler to do it. So I just go throw this proxy up, browse it, and then I have that data. This is more Spark focused. Usually I find when people come in to working with Spark, they're used to doing some sort of functional Python data programming where, say I want to validate emails or do, this common function, they go to they go look at UDFs. And if you've ever done anything with UDFs, it's like the data science is like, oh, well, don't use UDFs or try not to use UDFs. And really that has to do with performance. But really this is what this looks like. If you look at the diagram, what a UDF is I take my data and then, I write this function, and what it does is I just pull this column out, it runs that functionality against that column, and then it either inserts it back into the data frame, or, I just append a new column, if I want to do some sort of comparison analysis. So procedurally it looks good, but under the hood, there is some badness or some things that will kind of turn into gotchas if you're not careful. So there's two flavors of UDFs in Python, at least. There's just normal, I just write a normal Python function, throw data on it. And then there's pandas UDFs, where things get processed, in a data frame, it's very similar how you would just use, Python pandas. However, normal UDFs, there's this problem where they have to take Java structures and shuffle those into Python structures before you can actually do that function. And shuffles are really, really bad in big data because they just take, tons of time. And then when you're done, you actually have to convert that back to Java structures. So it just takes a lot of time, and that's really why they tell you to avoid them. The other thing, and like I've run into this a couple times, there's no guarantee on order. So if I'm processing data and it's the same column and I'm stepping through my code, like it may actually skip something that the next stage is needed for, because there's no guarantee on UDFs that they're going to actually be done in order. So that's definitely problematic. You're going to land with, you're going to land in some processing expecting this to already be done, and it's not going to be done. So when it gets to the end, it's not going to be kind of what you expected. And that's really, like, things like that are really the main case for doing metrics in your processing code. So you can kind of better understand, where the mistakes are at. So the good, if you do use pandas UDFs, they use Apache Arrow. So it's just in-memory transfer of data. So they don't have to actually do the shuffles. It just sticks it into memory, and like both are Arrow enabled. So, I drop it off, I pick it up, and everything's good. But then you run into this problem where you have to account for the Python memory as well, which really isn't easy to do, because you go into Spark and you can troubleshoot the Java side, but the Python side, who knows what's going on. A lot of times if it is like memory exhaustion, you'll get errors back that are good indicators, but sometimes it's just not clear where things are failing. So one thing with UDFs, they're great module wrappers. So if you've got something that's just, you know, I want to take this string and I want to convert it, say I want to create UUIDs or some functionality Spark doesn't have, Pandas UDFs actually work really, really well for that. They let you extend out, you know, some of the standard Spark library functionality. Transforms, these are actually standard Spark library. I put them in here because I don't really see people talk about them at all. Like I know people that have written Spark for 2 years, 3 years, and they've never heard of transforms. And I just don't really see a lot of content talking about them. So kind of the concept behind Spark transforms is I take this data frame and then I've got some processing steps, you know, against a single column, and then really it spits out a new data frame. So if you start in the bottom right, I have this data frame, you know, say I want to process names, you know, I may want to do lowercase, clean some characters, do some standardization, you know, filter out bad names. And then I have, you know, new data frame with that clean data. But what if I have 3 columns worth of names? I have to write that code out 3 times. So kind of looks like this on the left side. So this is kind of normal, and this is just 1 column. But if I have to write that 3 times, and then I also have to think about, well, what if the regular expression in there changes? Then I have to go to all that code and make all those changes. So like scaling this across multiple sources, it just becomes really, really difficult to track. So on the right side is what the transform looks like, where I just stick it in a function, and then the bottom is my code inside the actual processing code. So you're kind of creating this way to more functionally work with that data. So if my regular expression changes, I go change it one place and I'm good. Any resolution? So generally what I've run into with entity resolution is technique is, you know, I've got this massive data frame or table of, you know, say, you know, person entities. And then each row or each column represents an attribute of that person. So we just run similarity scoring across all those columns, and then the rows that have the closest score, same entity. Definitely works, and there's frameworks that scale this. The problem you generally run into is, you know, it takes a lot of compute, and then if I add new data, I have to rerun that again. So, you know, does it make sense to run all this compute against, you know, tables that are terabytes big for 2 rows? I mean, if it meets your Intel requirement, that's definitely what you want to do, because you kind of need to know, but it's just a lot of resources. So another way to look at this problem, or another way we've looked at this problem is, well, let's take, you know, kind of strong identifiers or attributes across entities and just graph them, and we'll see, you know, if I use the same email, you know, there's a conclusion that I'm the same person. The problem you run into here is, you know, data is not created at the same time, and people don't keep their phone number for life. So, you know, it's a semi-strong identifier, but, you know, it's definitely not a smoking gun. Same with email. You know, an email, multiple users. So these will get you close, but again, it may not be the precision you need. So, you know, looking at this another way, you know, how do we reduce the compute but still use the technique that lets us do it maybe a little bit faster? So if we graph it first, you know, we end up with this much smaller data frame that then we can run, you know, that same attribute analysis against and figure out score-wise, you know, is this the same person? If it's not, you can start, you know, actually breaking out those entities. All right, geocoding. So in my experience in OSINT, you know, geocoding is, I get this location, I put it into Google Maps, Bing Maps, whatever maps, and I get my location back. That certainly works, but the problem is it doesn't scale very well. I mean, even a million lookups, you know, if you get a lookup every half second, it's still something like 6 days. It's like 5.75 days or something. So, I mean, if you have that kind of time, great. I have a feeling it's going to scale more than 1 million rows at some point. So it becomes, from a time perspective, it becomes a little expensive, but it's also just cost expensive if you go look at pricing for querying those APIs. So, there's definitely like this resource constraint in scaling those locations. So, one of the questions that, I've been trying to ask and get a good answer for is, how do we use NLP or vector search to make taking this string and geocoding into actually something that you can use analysis-wise for correlation? So we actually had to chain this. There's a tool called libpostal. Off the top of my head, I believe it's written in C++ maybe. So, you compile this thing, and what it is it uses this NLP model that's trained on OpenStreetMaps. So, it kind of addresses the first problem you have. What is Brooklyn? You know what it is because it's natural language. So you kind of understand it's a city district, but doing analysis, using the frameworks that are out there, like it's just a string. So, I've got these 4 strings. I need to actually break those out into usable attributes. So, that's what libpostal will do to you. It'll take you this first mile. It doesn't normalize, you notice country here doesn't actually match up, but, there's ways around that with, keeping kind of enrichment tables. That's more about operationalizing your data. So then you just try to get everything to match as close as you can. Then we actually take these and feed them in a tool called Nominatum. Nominatum is really just open source Google Maps, and you can build your own server. So, you run this Docker, it pulls down the planet. I mean, you have to have a pretty sizable server, but that's potentially going to be much cheaper than running millions and millions of lookups on Google Maps. So you build this server, you've kind of done some of the initial normalization. So the strings in the gray are what you feed in, and then you get actual geocoded data back out. So now you're able to actually make more sense of this location data, different hierarchies, and you can kind of drill down, one actually gives us, this very tight location. Then phone numbers. Phone numbers are usually really messy because it's generally, at least the data I've looked at, user input. So you say, hey, give me your phone number. May have a country code, probably doesn't. May have, any number of characters in between. I hadn't actually seen this, and till we looked at some of the OSINT data sources, people put extensions on them sometimes, which was kind of a new trick. So kind of understanding those things to clean them up, because if I just strip characters out, I'm stuck with, extensions in there as well. So, how do we approach trying to do this at scale? Because again, it's a lookup problem where if I need to look up 1 million phone numbers, I'm kind of stuck at 6 days again, 5.5 to 6 days. And there's definitely going to be a cost. Actually, let me go back real quick and talk about, so one of the initial things I looked at was, could we use a UDF to do this? There's actually a Python module called phone numbers. Initially, it's not speedy, and I ran into some normalization problems inside of it. So if you pick away at the project, I think it's just dated information. So still could be a potential solution depending at your scale, but you still have to do some underlying normalization. And we can definitely get you there faster. So Google has this library called libPhoneNumber. If you've ever gone to a site and registered, and it checks your phone number, it's probably using libPhoneNumber or some variant. Really what it does is it looks and says, is this phone number valid? So this is all held in a Google repo, or I'm sorry, a GitHub repo. So if you go look at the GitHub repo, you see that there's all these CSVs and they're all aligned by country code. So now we can take this data and build ourselves, more operationally, relevant data to try and make our other data better. So we create this table, have country code, what the national prefixes are, the lengths of the number, the ranges, how long those numbers are, maybe some pattern matching. The geos in here are kind of spotty. I don't know that I would rely on them as accurate geos, but there are some in there. So we take this and we create a data set, then we go bang on it. So round one was really just taking the strings. We at least had some countries associated with the data we were working with. So you can say, oh, this is a US number, so it probably needs a 1 on the front if it doesn't have it. So there's still some cleanup you have to do, but you end up with these strings. So let's compare them with the regular expressions. This works. It scales pretty horribly. I actually tried to take just all the phone numbers out to eliminate duplicates, and it still scaled pretty horribly. So it's like 1 million. It's going to take you, depending on cluster size, probably a couple days, maybe a week. So it doesn't really scale that great. So let's go ahead and change those strings to integers and see, are they inside this lower boundary or upper boundary? And this definitely works, like just straight Spark. This took somewhere from hours to days. It really depends on, how many numbers, duplicates, things like that. So definitely feasible. Like, I would say this is a win. We actually use a platform called Databricks. So we were able to get this under 5 minutes. So they use this technique called range joins. Kind of how it works is they build, this is where we add size to the equation. So you build this bucket and you're kind of telling Spark, here's how big the buckets are, or the size of the buckets, and it just aligns them, and it's really, really fast. So initially I didn't try this because if you look at the lengths or the sizes, I think there's something like 12 different variants. So I'm thinking, oh, we got to join things 12 different times. But the way they do it is just fast. So you just iterate the sizes, do the joins, stack them on top of each other. Less than 5 minutes later, at 1 million, you're looking at normalized phone numbers. And that's really it. I mean, I think the main point is I'm not a data scientist. I am an analyst. So, a lot of the big data science, techniques and tradecraft, you can just pull those off the shelf just like a data scientist would do and like use that to scale your processing in your OSINT. Honestly, not even just for OSINT. I mean, all these techniques, used them in insider threat, our cyber counter intel ops. You can use them in threat intel. And that's it. Thanks for your time, everyone.